Mhm. All right. Well, thanks a lot, Lorenzo, for inviting me to this school for the introduction. And well, hello everybody. It's only my actually second time in Florence at GGI. The first time was like in 2016 when I was probably about your age, maybe a little bit older. I was still a graduate student, and I was here for a conference on conformal field theory. And now I'm lecturing about conformal field theory. At the time I was pretty confused about what conformal field theory is, and I was hoping that maybe by the time I'm my age now, I'd be a bit less confused. So I guess I'm a bit less confused about what I was confused back then, but now there are just different things that I'm confused about. But so the point of one of the main points of these lectures would be like to give you lectures that I would have liked to hear maybe at that time. So So the main point of these lectures is to present conformal field theory as a kind of an organizing principle for quantum field theory. So let's first ask what is quantum field theory? And well, to be honest, no one really knows exactly what quantum field theory is. It's very hard to define it mathematically. So there is kind of a contrast between quantum field theory and other subjects like general relativity. So general relativity is some of the foundations of general relativity are pretty well defined, pretty finished. So you know exactly what you're doing, but we don't really have a well defined mathematical framework to do quantum field theory in general. So I think that makes quantum field theory very exciting. But in general, quantum field theory is somehow a subject for treating kind of continuous systems with fluctuating degrees of freedom, which can vary from point to point continuously, and that's hard. That's hard to do because we often encounter problems with UV divergences. So if you want to define quantum field theory, you typically cannot really define it directly in the continuum, but you have to start with some theory with a UV cut, for example, on a lattice, and we'll see many examples of that as we go on, and then kind of define quantum field theory indirectly by taking the continuum limit of this theory with a cutoff. By the way, I should say that even though we are going to have a Q&A session in the afternoon, you should feel free to ask questions at any point in the lectures. Yeah, so I hope I hope to kind of tell what you already know by your lectures, so I can kind of also adjust the material. Right, so somehow the reason why quantum field theory is interesting is that the space of QFTs is in some sense finite dimensional. If you start with a theory with a UV cutoff, so on a lattice, there are infinitely many possible couplings that you can write down on the lattice. But once you take the continuum limit, only finitely many of these couplings survive. So somehow out of this huge infinite dimensional space of kind of pseudo QFTs with a UV cutoff, you only land on either a discrete set of points, which will be the case for conformal field theory, or some finite dimensional spaces of QFTs, which correspond to these RG flows between them. So that's also what I'll explain. So I usually understand things through examples. So let me start the lecture by some of the simplest example possible, which illustrates how we obtain a quantum field theory in a continuum limit from something with a UV cutoff. Is the example of the free scalar. So it's really the super simplest example that you can imagine. So free scalar on the lattice. But somehow the general idea is to start from some theory of a UV cutoff. This theory is going to have some parameters, and ultimately we want to end up with something defined in a continuum. So we'll want to scale the lattice to zero size. But we only get something interesting for some special values of these parameters. So this is called the critical behavior, as we are going to see. And free scalar exhibits already all of these things that I just said. So let's really start in the simplest possible way. So let's consider the. Oh, sorry. I guess I haven't described the outline. Oh, fine. Let me talk about the overall structure of the course so that you kind of have an idea where we are headed. Yeah. So this first two lectures today are going to be about this kind of general blah blah about the space of quantum field theories and why quantum field theories are interesting, how they organize our understanding of the space of quantum field theories, and this will be illustrated on the example of the Ising model and the Owen models at large n. Also, an important aspect of it is the renormalization group flow, which we'll cover today. After that, I'm going to talk about conformal invariance, first in general dimension. So conformal invariance is somehow a principle that you can use to talk about quantum field theories directly in the continuum. So that's kind of what we eventually want to do, to really work directly in the continuum limit, because as we'll see, dealing with UV cutoffs is annoying. And then we'll talk about the conformal bootstrap, which is a very precise, kind of axiomatic, and also computationally very powerful definition of conformal field theories, which works in general dimension, so also in general D. However, even with the conformal bootstrap, it's often difficult to make progress in general D. So eventually we are going to specialize to 2 dimensions where even more can be done. So 2D CFT is a kind of a very rich and kind of more or less manageable subject. And in particular, we can use the conformal bootstrap in that case to give exact solutions of specific classes of 2D conformal field theories, which are called the minimal models. But ultimately, we are interested in also in quantum field theories which are not necessarily conformal, and it's possible to illustrate this idea very nicely in 2 dimensions by constructing sort of integrable exact RG flows between minimal models. So that's supposed to be the culmination of the lecture series, to really see a kind of a live hands-on example of actual quantum field theories defined directly in a continuum with no UV cutoffs, which nicely interpolate between pairs of conformal field theories. So that's the idea. But now that well, are there any questions about the outline? Okay, so now let's really start and get our hands dirty with some specific examples, specific calculations. So what's the free scalar? So we are going to start on a lattice in D dimensions. So ZD is just the regular square lattice, right? Integers in D directions. D is the dimension of space-time. So for now, everything is going to be Euclidean. So some of what I'm trying to describe is a discretization of a Euclidean quantum field theory. But eventually, when I talk about conformal bootstrap, we'll see that there is a very important interplay between Euclidean and Lorentzian aspects. So eventually, we are going to go to Lorentzian signature as well. But for now, we are Euclidean, so Euclidean ZD, and actually, we're going to use periodic boundary conditions. So, we have this lattice, so I'm just going to draw it in 2D. And we are going to restrict our space to sort of n sites. So the linear dimension is n, and we are going to impose that everything is periodic in this direction with periodicity n, which means, so n is the periodicity. Which means that really we are working on the quotient of ZD by n ZD. So you can think of it as like 2 abelian groups, right? So we are kind of rescaling ZD by a factor of n and defining all of our fields on this quotient. And oh, okay, this when I do this, okay, I don't think I want it to happen. So we are going to introduce a field variable which as everybody calls a field phi, so I'm gonna stick to that convention. It's field phi where x lives in our spacetime, our Euclidean spacetime. So Euclidean spacetime now is just this quotient. So x is a point in ZD, and well, so phi of x is the same thing as phi of x plus n y for any points in ZD. Right. So this is what it means. This is what it means that it's periodic. Okay. Can everybody see what's going on up there? Okay. Okay. So so our space of fields is quite small now, right? It's certainly much more manageable than the one in a continuum quantum field theory. The space of fields is just, or space of field configurations, is just, well, did I say real? Okay, so phi is a real variable. So at each point we have this, and we have n to the d of them, right? There are n to the d points in the quotient lattice, and at each point we have r worth of degrees of freedom. And what's a quantum field theory? Quantum field theory is a measure, is like a probability measure, or yeah, it's just a way to do integration on space of fields, on space of field configurations. So what's the measure now? We are going to specify a measure. So this is how it's usually written, but don't worry about the notation. The measure is right. So what's going on here? It's supposed to be a measure on the space of these maps from our lattice to R, and d phi is just the flat measure on a single R. So you can kind of for each point we have the flat measure integrating over phi, and then there is some interesting factor out in front, which is mostly specified by the action. So S is the action, the Euclidean action, which for the free massive scalar that I'll talk about takes the following form. So we have like an integral over, well, this is an integral over space, or discrete sum over our space-time of a kinetic term. The kinetic term is just a discretized version of the usual Laplace, or usual second derivative squared. Right, so okay, and EG is the unit vector in direction J. Yeah, so we have this phi at each point in our periodic lattice, and this is some discrete derivative connecting two neighboring lattice sites, and there is some mass term here, or some kind of a coupling. I mean, you can also just rewrite this in a way which makes it look a little bit more like lattice models that you may be more familiar with. Basically, this if you expand this square, then you're going to see a kind of usual nearest neighbor coupling, like for example the one that you know in the Ising model, and then the other two terms, this one squared and this one squared, can be combined with that. So let me just write it. So we have. Right, so if we take here the cross term, then you get a, oh, let's do. So that's just the cross term, and then like that. So right, because we have this thing squared and this thing squared, but this thing squared is just, it can be shifted because we can always shift the summation over x by this unit lattice vector. So this thing squared and this thing squared gives you the same answer, and there are d of them. So it just shifts this constant g by 2d. Okay, is that obvious? Or okay, so this is just a finite dimensional integral, right? So it's an integral over n to d variables, and this integral is finite. Okay, who can tell me when is the integral finite? If we compute, suppose we just integrate over all of these variables, phi. This is, can anybody see? So it's a constraint on g, right? If g is positive, right? If g is not, first of all, if g is negative, then there are clear negative directions in the integral, and if g is 0, then there's a constant mode. We can shift all of phi's by the same amount, which gives us infinity. So, but as long as g is positive, then the integral is finite, and we're going to choose. You're going to choose this constant z over there to normalize it, so that the integral is actually 1. So this is what we. Okay, is this? Do you guys have any questions about anything that I've said so far?
Yeah, sorry.
Mm-hmm.
In the definition of the measure, if I think about the quantification theory, I have the d, and okay, the product of the small d is fine.
Mm-hmm.
Typically, you don't insert an exponential of the action in the definition, right?
Mm-hmm.
It's not essentially really the same measure.
Yeah. So in the right, that's right. But it's just a matter of notation, right? It's true that in most textbooks, when people write. In most textbooks on quantum field, it depends if you're looking at more like physics or math textbooks, but in most physics textbooks, what people denote d mu phi is just this part. So this is kind of the continuum limit of this part. So just kind of the flat measure is what often textbooks denote d mu phi, but I think it's, well, ultimately we are talking about a measure on some space of fields, which includes the e to the minus s. I mean, e to the minus is really a part of the, it's part of that. For me, quantum filter is a measure on a space of fields, and the measure is this whole thing, right? Because it's a positive thing. So I'm just choosing a notation where this notation also includes the e to the minus s, so it already has everything in it. Does that? Yeah, but good question. Yeah, that's right. So all right, and what's the point of this? So it's just a finite dimensional integral, and we can do it for it's kind of quadratic in the exponent, so we can compute correlation functions. So that's what we eventually want to do, right? So goal is to compute correlation functions. And well, what are correlation functions? Sorry. Well, correlation functions are just expectation values with respect to this probability measure. So I should say, if we well, the term for a measure that's normalized to 1 is a probability measure. Right? So now d mu is means that the total probability of everything to happen is 1. And correlation functions are just expectation values of various observables with respect to this probability measure. Yep. Sorry, why do I need G positive? So if imagine, I guess imagine that we try to do this integral. So we just integrate over all of the phi's. Then there's going to be a direction where all phi's take the same value, right? So I can kind of just go in the direction in the field space where all phi's take the same value, and then this term is 0 because they're all the same, and then this term is going to dominate. So if G is, sorry, there's a crucial point that there is a minus sign over here. So if G is negative, this thing is going to grow and it's not integrable.
Why is just considering the phi constant sufficient for this?
Right. So it's sufficient. Considering the constant case is sufficient to show that that the measure is infinite, right? Because I mean it's a finite dimensional integral. So if there is any direction in the field space where things grow like e to the phi squared, then it's kind of, yeah, basically it's something like this, right? You have, if you write in, well, right, if you integrate over all of these phi j, so imagine phi j are integration variables, there's some number of them, and if any of these alphas are negative, the integral blows up. Yeah, so that's exactly what's going on. If G is negative, then one of these alphas is negative, so the integral blows up. If G is positive, then that integral is cut off in all directions, right? So if you kind of imagine varying all of the phi's independently, eventually it's cut off by this positive G. Yeah, thanks. Yeah. It's a necessary and sufficient condition, right? So if it's necessary because if G is not positive, there is a direction where the integral blows up, and it is sufficient that because if G is positive, then the integral is cut off in all directions and therefore is finite. Yeah, good. Okay, so what are correlation? More questions? Okay, what are correlation functions? Well, correlation functions are just kind of expectation values with respect to this probability measure, and that's the way to write it is just so we can insert phi's at any point of our lattice and then integrate with respect to our, if you wish, path integral measure. Right, so this is just a definition of the angle bracket. So when I write a definition, I usually put like equals with that sign, which I guess in English is called colon. Yeah. Right, so like somebody asked before, I'm putting e to the minus s part of the measure here. But the point is that what do we want to do in general? We have some lattice model. We want to study as a function of the parameters and see if something interesting happens at long distances, because then we want to take the continuum limit, and we can only get a nice continuum limit, an interesting continuum limit, if some interesting physics survives at long distances. In the case of this theory, we can just compute explicitly all the correlation functions because it's so simple, which won't be possible in general. But let's just do it in this theory to see, to see what kind of behavior we can get at long distances. Okay, so solution of the free scalar. Right. So the way to the way to solve Gaussian integrals, so it's just a Gaussian integral. Gaussian integrals, they kind of look like e to the minus aij phi I phi j, where a is some symmetric positive definite matrix, and phi I phi j are your integration variables. And the way to solve such integrals is to diagonalize this matrix. So to choose a basis in the field space which diagonalizes aij, and for a theory on a lattice, that basis is just momentum space. Right, so we go to momentum space. But because we are on a lattice, the momentum space itself discrete. This really going to momentum space means performing so-called discrete Fourier transform. So what this looks like is that we're going to Fourier transform our field. So now phi hat is just some linear combination of the phi axis, which is defined in this way. So we are going to, instead of integrating over all of space, we are just summing over all our lattice sites. So this is just some finite sum of e to the I p dot x phi x. Right, so this is our discrete Fourier transform. And so what can we say about this p? So first of all, x is always x is a bunch of coordinates in z. So that means that p is periodic with periodicity 2 pi, right? So how do we? I mean, if I change p to, let me write it this way. Let's say p tilde. Right, so if p tilde is any vector which is an 2 pi times a vector of integers, then then this is true simply because we are summing over x is just a vector of integers. So if you take an inner product of a vector of integers and a vector like this, then the e to the I pi x stays the same. Right? So we have this identity. And furthermore, we are on a finite lattice, so because everything is periodic, which means that we can only work with a discrete set of p's. So really, p lives in this lattice, so it's like 2 pi over n zd. Right, so the set of allowed momenta is itself discrete because we are on a finite lattice in the x variable, and the inverse, we can write the inverse, which takes this form to the minus d. Okay, so let me call this quotiented lattice pi n. So the inverse Fourier transform is a discrete sum over points in this pi n of now e to the I px phi hat of pi. right? And the way to see this, the way to see that P is quantized itself is because X is itself periodic, right? So somehow the fact that P lives in here implies that phi of X is the same as phi of X plus Yn. Okay, and you can convince yourself that this is the right normalization, right? If you kind of plug this, for example, if you plug this formula into there or the other way around, then by essentially doing the sum over e to the I px, you see that you need to normalize everything with this factor. Okay, are there any questions? Yep.
Why is considered the spacing of the line?
Hmm?
Why is considered as the spacing of the line?
This y? Oh, sorry. Yeah, I should. So this should be true for all x and y. I didn't. Yeah. Thanks for the question. I didn't. Right. Right. So because we are putting periodic boundary conditions in space, so the periodicity, there's some kind of a duality between position space and momentum space, right? Periodicity in position space is equivalent to discreteness in momentum space, and discreteness in position space corresponds to periodicity in momentum space. So that's kind of what's going on. So we have a discrete sum on both sides, and yeah, P is discrete with this spacing because our position space lattice is periodic with this spacing, and vice versa. If I say one more, I'll probably get completely entangled into it. But hopefully, if it's not clear to you, it's fine. But you just think a little bit about what's going on, and you'll yeah. Okay, I think there's some longer chalk. Yes. So can you speak a bit louder? I didn't. What's going on? Is there no? So the lattice is just it's a unit lattice, right? So ZD means that all coordinates of x and y are integers. So my lattice spacing is 1 in position space at the moment. At some point we are going to take a continuum limit, so we'll try to rescale the lattice down. But for now, it's 1. Right, so that's what I mean by ZD. That all of them are integers. Does that answer your question? Well, for now, space is dimensionless. We are, integers are dimensionless. They don't carry any weight, like any mass dimension. So yeah, we'll talk about scaling dimensions when the time comes. Okay, so now when we go to this now the point is, once we substitute this phi into the action, then we get a formula for the action which is diagonal in our integration variables. So you can, you should convince yourself, this is an exercise, if you wish, that and again, yeah, that pi of n is just this lattice defined over here. You can convince yourself that the action becomes diagonal and looks like this. So there's a sign. 4 times sum over j sine squared over pj over 2 plus g. And here we have phi hat p, phi hat minus p. Right. So once we go to momentum space, there's just this nice diagonal object, well, almost diagonal because it couples the momentum and the inverse and the negative momentum. But that, so if you wish, exercise. Right after here, this is sine squared. Yeah. So there's a sine. So we are on a lattice, so we don't get like the usual p squared that we would get in a continuum, but instead of p squared, we get sine squared. And okay, the second part of the exercise is that the 2-point function now in position space. So the 2-point function in momentum space is the inverse of the kinetic term in momentum space. So this is the kinetic term in momentum space, which means that the 2-point function in position space is just the Fourier transform of the inverse of the kinetic term. So what does that look like? Well, the Fourier transform has this factor. Now we are summing over the momentum lattice. By the way, is my handwriting big enough, or should I write a bit bigger? It's okay like this. It's fine. Plus G. Okay, so maybe I should say 1 and 2. Right, so far we are just doing finite dimensional integrals. So this phi x1, phi x2 is some finite dimensional integral, and by doing kind of usual tricks with Gaussian integrals, or with free theories, you arrive at this expression. In general D, this sum cannot be done, but it's a fairly nice and compact expression, which has a lot of the physics of this theory. Now you can also ask, what about higher point function? So higher point functions in all free theories, so theories that have a quadratic action, they are computed using Wick's theorem. Are sums of Wick contractions, right? So an example of that would be the 4-point function. So let's this here has a Z2 symmetry, which means that all of the correlation functions of an odd number of phis will vanish because you can send phi to minus phi and it should stay unchanged. So odd point functions are 0. So besides the 2-point function, the next simplest one is the 4-point function, and it's a theorem in free theories that 4-point function is a sum over the 3 possible contractions. So maybe I should write it explicitly. There are 3 possible ways to pair. Okay, well, and so let me just write it schematically as 1, 4, 2, 3. Hopefully that's clear enough. And so essentially, the formula. Once we have a formula for the 2-point function, that formula determines all of the higher point functions using Wick's theorem in this theory. So basically, we have completely solved this free massive scalar on the lattice. Great. And that's pretty much as far as humankind's ability to solve quantum field theories go. I mean, there are very special quantum field theories which can also be solved exactly, but this is kind of the main example in some sense. But as the course goes on, we'll see various other examples, but this is really the prototypical example. Okay, but now we want to take the continuum limit. But before taking the continuum limit, we actually want to work in infinite space, right? So because I want it to be super precise, And we're working with finite dimensional integrals. I also made the space periodic, but we don't have to do that. So we can now remove this IR cutoff. There are two cutoffs. There is the UV cutoff because we are on a lattice, and there's the IR cutoff because we are working on a finite lattice. So let's remove the IR cutoff by sending n to infinity. Okay, solution of the. Maybe before I do that, let me pause for questions. Okay. Maybe I should say more about why we are doing what we are doing. So, basically, quantum field theory is very hard to define in the continuum. So I want to show you that it arises from very down-to-earth objects, namely just finite dimensional integrals. So quantum field theory is basically a very carefully tuned limit of finite dimensional integrals. Yeah.
Looking at again at the measure,
Uh-huh.
it's finding how much G is positive.
Uh-huh.
What plays the role of the mass here, I guess. So
Right,
it's
right.
somehow, probably this interpretation of the field space, maybe just with massive scalars in this case, right? That's the thing. I can rephrase the sentence in this way.
Yeah. So, well, okay. I'm not sure if I'm answering your question, but once we take the continuum limit, G will indeed become mass squared. So the continuum limit, as we'll see, the continuum limit is just the free massive scalar, where G is m squared. So, but that's kind of the point of this first lecture, to show exactly how it goes. So let's remove the IR cutoff. And this is already non-trivial, right? Because we are going from a situation where we're doing finite dimensional integral that is totally well defined to an infinite dimensional integral. So we are sending n to infinity, and instead of working on this periodic lattice, by sending n to infinity, basically this quotient goes away. So we end up with an integral over phi of x, where x can take infinitely many values. But there is no problem with that. Even mathematicians are happy with this. We are not mathematicians, so we don't have to prove things exactly rigorously, and we can just look at what happens to the formula for the 2-point function, because in this formula you can take the limit in a completely smooth way, right? So what happens as we take n to infinity? We have this lattice Pn. So let me just write it. That sum over momenta is a sum over this lattice. And what happens as n goes to infinity is just that the momentum space, the discrete momentum space, becomes denser and denser, because here is 2 pi over n, so the spacing in momentum space becomes denser and denser. And this discrete sum becomes a continuous integral in that case. So this another sort of exercise is that in the continuum limit, our summation measure in a 2-point function in an absolutely smooth way becomes the usual integration measure in momentum space. But notice that the momentum space is still periodic. So this n goes to infinite limit makes it denser and denser, but it doesn't remove the periodicity. The periodicity in momentum space is there because we are working on a discrete lattice in position space, and we are not changing that. So this integration is still over. It's basically over, minus pi and pi in all directions. So it's this is supposed to be. Right, it's a d-dimensional integral where each of the momentum coordinates is integrated from minus pi and pi, and the integrand is periodic in each of the coordinates with periodicity 2 pi. So this is kind of the reason why 1 over 2 pi d appears naturally in all of the momentum space integrals. I mean, what's the basic idea? Why do you get this 1 over 2 pi d? Well, so the essentially what happens here is that dp dp is essentially like 2 pi over n dn, where n is the variable that's changing by steps 1. So dn is kind of the variable over here. Well, okay, I'll probably mess it up. The way you can think about this is that it's n to the minus d, and instead of a sum, you have an integral of dn, where n is the variable that's changing with unit steps, and momentum is 2 pi over n times this variable n, which is changing by steps 1. So dp is 2 pi over n dn, and once you substitute for dn into this formula, you arrive exactly there. So anyway. Yes.
We say because we're going to continuum, we're only going to consider the limits of the 2-point function. We're not going to. We're going to compute everything to get 2-point function and then take the limits. We're not going to take the limits any earlier.
Okay, good question. So we are going to deal with all correlation functions by saying that the Wick's theorem holds all the time, right? So it's going to be true no matter what is the lattice spacing, no matter whether we take n to infinity or not, that higher point functions are computed using Wick's theorem, which means that once we have found a 2-point function, all the higher point functions are fixed in the same way. So yeah, we will know the full solution of the whole quantum field theory. Does that answer your question? Yeah.
Yeah, I guess more like you could, in theory, take the limit at some other process, some other point in this calculation.
Right.
Are we only considering taking the limit right at the end, or could you get away with taking the limit earlier?
Good. Yeah. So one way to interpret doing what you're suggesting to do is to, well, okay. We are doing two-step process, or we are removing IR cutoff. So we should first try to define the measure on the infinitely many field variables on the entire ZD lattice, and that's fine. But then we could try to define the measure by taking the continuum limit. So now it's going to, instead of it being a measure, probability measure on the space of discrete functions from ZD to R, it's going to be a measure on some kind of a function space, right? Because now the functions field variables become continuous, and that's certainly possible to do in a case of a free theory. That is quite hard. In fact, it turns out that the continuum limit of the measure is not a measure on functions, but rather distributions. So one needs to be a bit careful, and this kind of thing has only been done for a rather limited class of theories. For the free theory, it's been done for massive 5 to the 4. It's been done recently. That program has been completed for Liouville in 2 dimensions, for Liouville CFT, but quite hard. So I prefer to just start on the lattice and then start talking about correlation functions early on and see how the limit works at the level of the correlation functions to kind of sweep all of these mathematical difficulties under the rug. So okay, but so far we have not gone to the continuum limit. Yeah. Oh, good. Yeah, good. Yeah, I think I was a little bit too fast over here. So let's just set d equal to 1 for now because everything works the same way in all the directions anyway. So you have to, this is the momentum space, and initially the momentum space is periodic. If period is 2 pi, and it's discrete, right? So we have n. So this pi n contains n points in this discrete momentum space, but it stays periodic. Now, once we take n to infinity, this becomes denser and denser until it becomes a continuous integral instead of a discrete sum. But the periodicity, same. So it's still 2 pi, and because everything is periodic, I could have written this as integral from 0 to 2 pi, or minus pi to pi is the same. Is that no? Uh-huh. Yeah, well, I guess the idea. Sorry. Is your question about how do we get the continuous integral from a sum that only involves rational points? Well, the idea is, I think the idea is what we are integrating is a smooth function. So if if the function that you're basically integrating is sufficiently smooth, then you can approximate the integral of that function arbitrarily well by summing it over discrete set of points and then making it denser and denser. Of course, this is not going to be true for, if you take a function which is 1 at all rational numbers and 0 at all irrational numbers, that's not gonna work because the integral of that function is 0 because the set of the measure of the set of rational numbers is 0, but my way of doing the integral would give you 1 because I'm only summing its values over rational numbers. But yeah, as long as the function is smooth, it's fine. And this function is very smooth. That's the one that we are summing anyway, right? This is just 1 over sine squared pi. It's good. Okay, so in the n goes to infinite limit, so far we've only removed the IR cutoff. We get the expression for the 2-point function. Okay, I think, which is now integral. And so the integrand stays the same, and the only thing that changes is that this measure becomes a continuous integral. Oh, sorry. And there's ddp to the 2 pi d. Right, so this is the 2-point function on the infinite lattice. So we have removed the IR cutoff. It's, okay. Okay, so now we have some kind of a statistical lattice model on the infinite lattice, and we can ask what is its behavior at long distances. So this is kind of always the question that you want to ask. We are kind of defining the model at short distances using some Lagrangian or some lattice Hamiltonian, and we want to study how the correlation functions look like at long distances. So we are long distances means that we are taking this vector and making it very, very large. And it turns out that the behavior depends very strongly on the value of this parameter g. That's essentially because this parameter g controls when this integrand is analytic. The regime in complex momentum space when this is analytic. And when g is large and positive, there's a contour deformation argument that shows that this expression decays exponentially in x. It was maybe actually, so is that clock correct? Okay, I'm going much slower than I thought I would be going, but that's okay. I mean, you're asking great questions. So let's take a 5-minute break, and then we continue after the break. All right, so yeah, some questions that I got over the break made me realize maybe I didn't say the things, some of the things the way I wanted to say them. But basically, the name of the game here is that we are trying to define a nice continuum limit, and to do that, we have to adjust some parameters in our microscopic lattice model. So let's see, and this is a very general fact about interacting quantum field theories. I can start with some interacting lattice model or field theory of a UV cutoff, and taking the continuum limit. If I want to take the nice continuum limit, then I have to adjust the parameters in some way. And it's just that in the free scalar we can do all of this explicitly, which is why I'm starting with it. But this general idea of adjusting parameters to get a continuum limit is completely general and works also for strongly coupled quantum field theories, as we are going to see in due time. But what do I mean by what do I mean by adjusting the parameters so that something nice happens? Well, the main question, like some of the fundamental question in quantum field theory, which we'll ask also in this model, is how do correlation functions how do correlators look like at long distances? Which in this case means that we are taking the size of x1 minus x2 very, very large. Right? And there is a so if you look at this integral, it may not be totally obvious, but there is a standard mathematical procedure which exhibits the large kind of distance behavior of this integral, and it's a very useful idea. So let me show you. Let me show them. Of course, some of you may already be familiar with this, but the idea is that for generic values of this parameter g, the correlation decays exponentially, and the reason for that is that integrand is complex analytic in complexified momentum space. So this is a very important idea, that kind of exponential decay in position space corresponds to holomorphicity in momentum space. Right? Sorry, let's stare at this integrand. When, of course, the integrand is periodic, as it should be. So it makes sense to integrate it because the sine squared is periodic with periodicity 2 pi, and the denominator is certainly non-zero when g is positive. So this is another way to see that g should be positive. It's a singularity, and in fact, it's complex analytic in some neighborhood of the integration contour. Right? Let's just imagine for simplicity that d is equal to 1, because this works the same in all dimensions. Then, well, this thing is non-zero as long as g is positive, and if we draw let's draw the complex p-plane. We are integrating from minus pi to pi, so there is 0. Okay, maybe let me just draw it on the other blackboard. So there is our complexified momentum space. There's 0, there's minus pi, and there's pi. So our everything is periodic under this shift by 2 pi. And the integrand is analytic in some domain up to some point. So let's imagine that we can that g is small, so that we can approximate this by p squared, right? So if g is small, the location of this first pole is at I times square root of g. I just imagine well, I guess that's probably obvious that basically we end up with p squared plus g. So the pole of that integrand is over here. And I guess there's also a symmetric pole at minus I square root of G, right? But that means that we can take our original contour. Okay, this doesn't work very well. We can take our original contour, sorry, and we can shift it either up or down up to this point. Okay, I think this was supposed to be a green color, but I guess it's pretty similar to white. And by doing so, you exhibit the fact that actually at large x, that integral is decaying exponentially. Right, so imagine we do that in one dimension. So in one dimension we would have minus pi to pi e to the I pi x1 minus x2 divided by this 4 sine squared pi over 2 plus g dp over 2 pi. So this is our original integral, but then let's shift. Let's shift p to p plus I let's say iq. Then if we do that, then we still have e to the I pi x1 minus x2, but we also get this factor of from the iq, so e to the I becomes minus, we get I to the minus q x1 minus x2, times something. But it doesn't really matter what we get downstairs. For this to work, q should be less than, in absolutely should be less than the square root of g, right? Because then we are not moving past the singularity. So we are kind of moving our integral to over here. And now let's imagine what happens when x1 minus x2 becomes large. When x1 minus x2 becomes large, well, nothing happens here, but this factor becomes exponentially suppressed. Right? And well, also nothing special happens here. I mean, the thing downstairs stays bounded. So this contour deformation exhibits the exponential decay of this integral. And since there is an upper bound on how far we can move the integration contour, okay, yeah, I made a change of variables. Sorry, so I did this change of variables. So maybe I should have written. So here p was real, from minus pi to pi, and here, so I'm writing. I'm moving the contour to, I guess, this, where now p tilde is real. Well, this real variable is now the parameter, is the real parameter along our new contour. Yeah. Okay. Sorry. This was a bit messy, but I can do it a bit cleaner. So we had the original integral, which was some integration where p was in there minus pi to pi. Then we move the contour, so p is between minus pi plus iq to pi plus iq, right? So this is our new integral. And then I'm going to write p as p tilde plus iq, where p tilde is again real and between minus pi and pi. So the thing that I'm integrating over here is p tilde. And q just showed up in this exponential. That's a good point, but you always, well, what's happening here is that we want to show that that the integral is bounded by something. So you always want to, you kind of always want to choose, you always want to choose the contour which gives you the strongest bound. So the integral gives you the right answer no matter where you shift the contour, as long as you don't cross any poles. But it may not be obvious from staring at the integrand what is the true asymptotic behavior. You want to shift you want to move the contour down when x1 minus x2 is negative, right? x1 minus x2 could be either positive or negative. And when x1 minus x2 is positive, by shifting the contour up, you exhibit the right exponential decay. If it's negative, you want to shift it down to exhibit the exponential decay. Anyway, the conclusion here is that this two-point function is bounded. So let me write it like this. This is not supposed to be very precise. Is bounded by exponential of minus square root of g, and times the absolute value of x1 minus x2. So this is the argument that I was just saying, that no matter whether x1 minus x2 is so s this x1 minus x2 goes to infinity, right? And also the argument was completely general. If you have some expression for a two-point function in momentum space, and if that momentum space formula is analytic in some strip around the real axis, that means that in position space the two-point function is decaying exponentially, again by shifting either up or down. But you can see that something special is going to start happening as we decrease g to 0. Now that's of course what we want to do. So we want to take the continuum limit, and now we see that when g is positive, at long distances we don't get anything interesting because all the correlation functions eventually die off exponentially. If we through the continuum limit, we can either rescale the lattice to some small size and keep the positions finite, or equivalently you can just keep the lattice fixed and take the distances large. And to get something interesting in continuum limit, we see that we should scale g to 0. Okay, so let's actually okay, let's see what happens when g is 0. Good, yeah. So as an exercise, you can try to figure out this higher dimensional contour deformation, but what you get is the same answer, where now x1 minus x2 is just the norm of the lattice vector in d dimensions. Sorry, who asked the question? I didn't. Oh, over there. Thanks. Right. So, well, I guess I can tell you that in this case, what you want to do is you want to shift the integral to p plus iq. So now p is a vector, right? Well, I haven't been writing the vector signs, but well, p plus square root of g times n, where n is the unit vector in the x1 minus x2 direction. So n x1 minus x2, right? So in this case, this shift is the optimal choice, which gives you the fastest fall off, and then you get the same answer. Okay, so what happens? Of course, earlier I was telling you that g equals 0 is not really a good point because there is an infinity, but it turns out that you can still define this limit in a continuous way because the two-point function makes sense even when g is 0. Right? If you look at it, when g is equal to 0, then this integral is finite as long as dimension is greater than 2. So there is no UV singularity, but there's a singularity at p equals 0, which looks like d to the dp over p squared essentially, and that integral is finite as long as d is greater than 2. So there's no problem with taking that limit. And so what is the answer in this case? So when g is 0, right? So let's write this as e to the I pi times the unit vector in the. Okay, let's write x1 minus x2 as the unit vector in the x1 minus x2 direction times its norm. So r is the norm of the vector. And as we take r very large, this integral becomes kind of more and more dominated by the region of small p. So let's actually change. Okay, the way to do it is to change variables. We're going to define a new integration variable. Let's again let's call it p prime, which is this p times r. So once you change these variables, you get minus pi r to pi r, e to the I pi p prime dot n. And this is p prime j over 2r. And the measure picks up a factor of 1 over r to the d. Right, so I'm just changing variables. And now as we take r large, what happens? Well, this becomes integral. So as we take r to infinity, this becomes an integral from minus infinity to infinity. So I'm just going to rewrite 1 over r to the d minus infinity to infinity. Then nothing happens in this exponential. So it's just e to the I pi because there's no r. And as we take r very small, very large here, then we can approximate the sine squared by its leading Taylor coefficient. So we get 1 over the 4 cancels 1 over 2 from the square. And we get sum over j, pj prime squared. And this 2 becomes a minus 2. So I guess, yeah. Right, so and now this is just a number. This doesn't depend on r. Right, so we have derived that at large r, the 2-point function decays like a power law, like 1 over r to the d minus 2. And that's the first time that we are starting to see conformal field theory in this course, because the essential feature of conformal field theories is that their correlations look like power laws. Or certainly 2-point function look like power laws. And okay, if you want to do the exercise, what is actually this coefficient is that, I guess all of these are kind of exercises that you want to do once in your life. So as r goes to infinity, this becomes some gamma factor 4 pi d over 2, 1 over r d minus 2. Okay, so that integral becomes just this factor. And you can also nicely see that something goes wrong when d hits 2. So we were saying that the integral diverges, and indeed this gamma function has a pole at d equal to 2. Okay. Mm-hmm. Yes. Yeah, that's right. So I was. In the result is you get the right answer. Yeah, it's a good point indeed. That at the boundaries of the integration we are not really allowed to use it, but the integral is still dominated. It turns out the integral is dominated by the small p. Well, but the integral is dominated by finite p prime. Is the right statement. Okay. Any more questions? Okay, so far the conclusion is that in this very specific model, for generic values of the parameter g, there's nothing interesting at long distances, and for special value of the parameter g, we get power law decay at long distances. And this is a very generic feature of everything in life. But because I keep talking about a continuum limit, let me say more exactly what I mean by the continuum limit. Because so far we've been keeping the lattice spacing fixed. Continuum limit, we can take it by rescaling the lattice. So now we are going to take the lattice to be all the multiples of A. So A is the lattice spacing. And, well, it's also our UV cutoff. And the continuum limit is achieved by taking A to 0. Okay. Now, it turns out that to get nice correlations, to get kind of correlations that survive in the continuum limit, we have to also define a renormalized field. So let's define this phi of capital Phi. To be A to some. I mean, you'll see why this power kind of naturally emerges from what I've said so far. Right. So phi was the field defined on the original lattice Z, and now X. So let's say X. X lives in the rescaled lattice, so eventually X is going to live in a continuum, but for now it lives on the rescaled lattice. We are dividing here X by A, so this argument still lives in the integer lattice, so we can just use all our formulas that we had before. And if we compute a 2-point function, of this field, I guess we can do it. So there's e to the d minus 2, an integral from minus pi to pi of e to the I pi x1 minus x2 measured in the units of lattice spacing, and then this sum sine squared over p over 2 plus g. So let's first set g to, if we set g to 0, we can again play this trick with rescaling. So now we can rescale, write p as a times p prime, and you'll see that as a goes to 0, okay, I think something is wrong. Sorry, this was supposed to be a okay. There's a minus sign. So I was missing a minus sign. So also here, there's a minus sign. Okay. So you can see that once we transform this, once we do this change of variables, you get a to the d, which cancels this a to the minus d over here, and then the sine squared is going to have a factor of a squared, which means that in the end, we just get integral from minus infinity to infinity of e to the I pi x1 minus x2, right, p x1 minus x2, over p squared, and dp to d over 2 pi. Okay. Yeah. So this is the first time that we see something in a continuum limit. The a completely dropped out, and we have defined a correlation function of this continuum field, which is finite for any non-zero x1 minus x2. Okay, is this? Mm-hmm.
Since we are taking the actual unit and the should we make some sort of operation
Yeah, good. So what are we holding fixed here? What we are holding fixed is the physical positions. So we're holding fixed x1 and x2. Right. So what we were doing before is that we were sending x1 minus x2 to infinity and keeping the lattice fixed. And now we are doing something completely equivalent, just in different variables. Is that we are keeping now this x fixed. So that's our position in the continuum. And we are sending a to 0, which means that, as I said before, the argument of the lattice field is going to infinity. But really this is the same limit. And this a is here just to make sure that the overall factor cancels out and we get a finite answer. Yeah. This integral, or yeah, this integral is finite as long as d is greater than 2. Yeah, so this integral is actually, sorry. Yeah, so that integral can actually be done in a closed form, and we've already done it. Well, I've told you what the result is, just in a different language. So when a is equal to 0, so in a continuum limit, that thing is equal to this pi d over 2, 1 over x1 minus x2 to the power d minus 2. Yeah. So it's the same thing that we saw over. Okay, I'm not sure. Oh yeah, so the r goes to infinity limit of the lattice correlator is the same as the continuum limit of the continuum correlator. Right. And again, if it's a good idea to go through these steps maybe on your own in more detail to see exactly what's going on, but really it's the two things are completely equivalent. Okay, I think he was first.
So what are we meant to learn from this? Like, fact that the R with limit is the same as the continuum limit. Like, what is the thing?
Well, that statement is kind of trivial. It's just a different way of talking about the same thing. So we are using the fact that for g equals 0, the correlations on a lattice are interesting at long distances to define a new object, which is a continuum quantum field theory, by rescaling everything.
But you don't expect this to hold in general, right?
No, the point is that yes, for general lattice model, there are going to be some submanifolds in the space of their couplings where their correlations are interesting at long distances. They go like power laws, and when we tune ourselves to the proximity of that submanifold of couplings, then we can define continuum quantum field theories in this way. And this is in fact how probably all quantum field theories arise. Yeah, you had a question. Yeah. Yes. Yeah, so that's not quite. So first we were on a lattice, and we had an IR and a UV cutoff, and we just removed the IR cutoff by sending n to infinity. Okay, and then IR cutoff is removed once and for all, and we can compute correlation functions at some at arbitrary positions, and we never have to talk about the IR cutoff. In particular, the distance between the 2 points on the lattice is not really the same thing as the IR cutoff in my discussion. Okay, so but we removed IR cutoff, and now we are discussing how do we remove the UV cutoff. Well, we just remove it. We can remove it as long as G is 0. If G were non-zero, then we would just get a 0 answer for our correlation functions. But we can do something kind of more general than what we've done, which is to keep G non-zero and send it to 0 together as we send the UV cutoff to 0. So let's do that. Yeah.
When you get G not 0, you would just get E minus G x minus x1 minus x2 in the bottom left vector.
Yes. Well, so yeah. Let's just see what happens. So if we keep G positive and fixed, and we go through these steps, then we would get something like phi of x1, phi of x2, is some power of a times the correlator. Yeah, maybe I should have done this in a cleaner way. Right. So this is what's going on, right? And now we want to send a to 0, which is the same thing as sending the distance between these two lattice points to infinity. And we have learned earlier that looks like square root of G times x1 minus x2, but now over A, because we have rescaled the positions, right? So what appears in the exponential is the size is the distance in lattice units. So there's 1 over A. And now you see, no matter what power we choose here, when we send a to 0, this just vanishes. Okay? So we don't get anything interesting. Yeah. If G is strictly positive and fixed, you get a trivial QFT with all of whose correlation functions are 0. But now you can do something slightly more general, which is to set G to a quantity which goes to 0 as A goes to 0. So we keep M fixed, and we still take A to 0. Okay, so let's see what happens in that case. Okay, I think. Right, so let's do it properly now, because this is really the most general case. So I'm going to show it to you step by step. So we go back to right. So what do we have? The phi has that power outside, which means that just from the definition of phi, we get a to the 2 minus d outside, and the correlator on the lattice, where the coordinates of the two lattice fields look like that. So let's continue. We have this thing out in front. Then we don't know what this correlator looks like. It's this integral from minus pi to pi of e to the I p, and the difference between these two numbers. So that's x1 minus x2 over a. And now it's 4, sum over j. Okay, I think I've written this thing too many times today. It's and now what? Now there's a g, but we are tuning g in this way. So let's already put it in. Okay, so now g is going to scale to 0. And we have d dp over 2 pi to the d. Okay, so what is the natural thing to do now? Well, we are sending A to 0, and there is P over A over here. So it's natural to rescale the momenta and write P as A times P prime. So we have A to the 2 minus D, and now the integral over P prime. So P prime is P over A, so it's minus P over A plus P over A e to the I P prime dot x1 minus x2 over 4 sum over G, this annoying sine squared, P prime J over A over 2A, right? Sorry, no, P, sorry, not over 2A, times so A Pj over 2 plus A squared M squared. Now the measure picks up a factor of A to the D, dP prime over 2 pi D to the D, okay? Okay, so far this is exact for any A. And what happens is that we can first of all cancel this A to the D with A to the minus D, and now we take A to 0, so the integral goes from minus A to infinity. Here we approximate by the leading Taylor coefficient, get A squared from here, another A squared, which cancels the A squared out in front. So this integral, as A goes to 0, just becomes the integral over all of Rd of e to the I pi x1 minus x2 over p squared plus m squared. I guess I should say p prime because that's what we are calling it. Okay, so a completely dropped out in this limit, and m is the parameter that we are holding fixed. x1 and x2 is what we are holding fixed. Okay. Right, so what happened now is that if we set G exactly to 0, we get something that has power law correlations. If we set G non-zero, we get nothing. And if we tune G as we go to A equals 0, then we can get something that's more general, which is of course the massive free scalar. So let me just call this the 2-point function as a function of x1 minus x2.